Welcome everybody. Thanks for joining us today. Today's topic, we're going to be doing designing wood buildings in RISA. And again, my name is Debbie Penko. Let's kind of start talking a little bit about the programs we're going to be looking at. RISAFloor and RISA 3D together, those two programs are going to be what we're going to be using to build an actual building model. So it's going to be a multiple story building, and the versions here that are going to be our latest versions here are version 7.0 for RISAFloor and version 11 for RISA 3D, and these are the versions we're going to be using today. Kind of to jump back a little bit more into the theory of wood design and wood building design, we're going to be basing all of our conversations today based on the IBC 2012, the NDS 2012 there. You'll see we'll use some of the wind and seismic provisions, but we have older codes available in the actual model, but what we'll be doing here is modeling on the latest codes we have available. To talk a little bit more about kind of the overview of what I wanted to discuss in this webinar is really going to go through the lateral load paths, building this building. Mostly what we're really concerned about in RISA designing the building is going to be the lateral design. That's going to be our major point we want to talk about. We'll talk about a lot of the gravity design as well, but really the focus will end up being, at the end of the day, we want to finish that lateral design of the shear walls in particular for our model. We'll talk a lot about how the diaphragms play with the modeling too. Diaphragm behavior is going to be dependent based on a flexible diaphragm or a rigid diaphragm, and how that really distributes the loads to our model. And then how the walls behave and how we have some different options in designing those walls and what that means for us. So if we go from there, what we can see here is that we can kind of talk a little bit about that load path. So we've got walls. We see in this model, in this diagram here, just kind of a schematic of how your building design would be. And we're going to be talking about wall wind loads as we apply loads to the structure. Those loads get applied into the diaphragm level. So in this picture, you can kind of see here that we've got the diaphragms at the roof level. We have diaphragms at each floor level. Those diaphragms will distribute those loads based on a wind load or a seismic load, but we apply that to the walls. It gets distributed through the diaphragm into the walls and into the roof, and then distributed through the structure all the way down into our foundation. So the diaphragm is going to be the loading mechanism in which it distributes that load. So how that load gets distributed is based on what kind of diaphragm you choose to use. As I mentioned, we have a flexible diaphragm and a rigid diaphragm. So I want to talk a little bit more about what that means when we are in a flexible versus a rigid. So in this whole schematic, we think about this wall wind load, and we take that more to a plan view here. As we look down on the structure, we see that we have shear walls listed here on the side, actually on the sides and the center here. The diaphragm is just around the entire structure, and we are applying a wind or seismic as a uniform load, maybe in this one direction, which is vertically on my screen. And we're just laying out how this plan view of this structure and ideally will be in theory here. So what we look as the next slide here, if we're talking about a rigid diaphragm, that uniform load gets distributed to those walls, and it goes into each wall based on the stiffness of that wall. So in this case, if we have these three walls, so we take the entire loading, which would be our just W loading of that uniform load, and distribute it based on the three walls. So W divided by 3. A third of the load is going to each wall, assuming that each wall is the same thickness, the same length, and basically the same stiffness. So those three walls get identical loading. That rigid diaphragm is distributing that load based on that rigidity of that fully rigid diaphragm. So that's kind of straightforward, but as we look kind of to the next one, we talk about a flexible diaphragm. So what is a flexible diaphragm? A flexible diaphragm, it is fully flexible. There is no rigidity there. So we have the ability here when we apply that uniform load just directly to our structure, same type of load we saw previously. And what we see in here is it breaks it into a quarter of the load into the outside, and half of the load is going onto this inside wall. And that's basically your tributary area of that wall. So we see that the load gets distributed half to that wall here in the center because half of that tributary area is going straight to that wall, and a quarter of the tributary area is to these outside walls. So we're breaking it down a little differently based on whether you're a rigid or a flexible diaphragm. And this is a simple model, but you'll see here we were talking about W over 3 in the previous slide for a rigid diaphragm, and we see W over 4 or W over 2, a quarter or a half. So you're going to see some different loads happening in those walls based on that diaphragm selection. Now, what's nice in RISA is we can bounce between the two, and I can show you that later on when we're building a model. We'll look at how it would be if we go with a flexible diaphragm or if we go to a rigid diaphragm. And depending on the configuration of the building, it may increase or decrease, just depends on what we're looking at. Now, as we go kind of farther, let's talk about how this can get more complex. So if we're looking again at a rigid diaphragm, and we see here that this rigid diaphragm here, we have a wall. These are not equal walls anymore. Okay, so we've actually made these outside walls where their stiffness is, let's ideally say, equal to 1, and we half that wall. We make that wall in the interior wall half of the length. So we say, okay, that wall is now half of the stiffness of those outside walls, and we connect this here with a collector beam here with a column. And we say, okay, that inside wall there is only receiving about half the stiffness with this the collector and that wall. So as we distribute the loads, what we see here is that the loads are going to be distributed differently. They're going to be based on the stiffness of that wall there. So we're going to see that only about 20% of the wind load there is going to be applied, or the seismic load gets applied to the center wall, and where we see about 40% of that load goes to the outside walls. Okay, and that's because of that stiffness. What we're basically doing there is saying this load gets distributed based on that stiffness. So we have to use that as an indicator. Now, for a flexible diaphragm, we can see the same configuration where we see that same collector element there. We've got the same half wall distance there in the center. And for a flexible diaphragm, it really is just basing it right off of the tributary area. So we still see the same information listed there as we did when we saw a full wall. We just see that, okay, and now we're going to get that tributary area distributed to the collector and the wall elements themselves there. Those are going to now see the uniform load divided by 2, or half of that uniform load, and then we're going to see a quarter of the uniform load again on the outsides. So still based on the tributary area. We're going to find how much tributary, considering that collector there is there to take the load as well. This would be considered a lateral element, so it's there to collect it as well. So we can kind of see it a little bit more. Now, when we apply this, now that was all in theory and how we just described how we apply loads in theory. What I wanted to show you guys is an example of what happens when it actually gets applied into your model. How do we see that visually in the model? So for a rigid diaphragm, when we assume a rigid diaphragm, we assume that there is a point right there in the center of mass that we apply that rigid, we put that load application right directly in there. So 1 point load goes into that diaphragm. And you can see here this is just a representative of 33 kips applied into the center of that model, and it's applied horizontally. This example I have. And if I look at this in an elevation view, that's applied at the diaphragm level. And what happens is that load then gets distributed behind the scenes to all of the wall elements. So when we run the solution, it's all attributed based on the diaphragm, and the diaphragm is rigid, so it gets all attributed to the wall elements in that direction, and in any direction basically, because it's rigidly tied there. So wall elements won't have very much stiffness out of plane, so really what we'll be looking with in-plane stiffness. But it will go slightly if we have some skewed walls. This rigid diaphragm will kind of attribute to those skew walls slightly. We've got all sorts of different elements happening in here, so we'll see that load goes attributed to that rigid diaphragm based on the direction of the load and the rigidity in that direction of those wall elements. Now, when we see a flexible diaphragm, same type of theory here. This is in the x direction, and this is in the x direction on the right, and the z direction on the left. The same type of theory. We apply a point load in there, and we can visually see that same point load. But for a flexible diaphragm, when you run the solution, we have something called a transient area load that gets distributed to help you understand how that point load broke it down from that one single point load into distributed loads. So if I kind of see here, this gets turned into distributed loads. Oops, there we go. Transient distributed loads is what we call them. And you can see that internally the program took that point load, and it's a horizontal direction here, point load, and we distribute it to the walls in the horizontal direction. Now, any of these skewed walls, they get a component of that because they are in that horizontal direction as well. So they'll see a little bit of that in these skewed walls as well. Does not need to be orthogonal. It can be in any different direction, and whatever component of it is in the X or the Z direction, it will get that component of load. But we see here in the X direction, we also do the same thing when we apply loads in that direction. So we have it in the X direction, we see that the loads are being applied to the walls that are resisting the load in that direction, and we're going to be basing it on the tributary area of that. So you can see that you've got these skewed walls up front. They have a little bit of load up there as well in that direction. Now, this is after solution, so when we run a model, we can verify this. This is just a very nice tool to see that you understand what's happening behind the scenes. So transient distributed loads, we'll see that in an example when I build a model from scratch. So let's go ahead and talk a little bit, too, about roof loads. So roof loads are designed similarly to what we just saw. This is assuming a flexible roof diaphragm. When you run the model, what you'll see there is you actually get, instead of a point load, you're going to get area loads. And this is what we're seeing here is a picture of area loads, and then this is actually uplift on our roof. And we see that the load is going to be, this is just one direction of the load there, is going to be pushing on one side of the roof versus the other side of the roof. And what that does internally is that turns that also into transient distributed loads, and we get to see that transient load distributed on that wall element. So all of these walls have, we can see that those distributed loads along their perimeters. And this gets broken up into the X and the Z coordinates, or directional loads there. So you're going to see that kind of combination of loads applied into that wall. So you get to see that uplift right there. Very similar to a floor load flexible diaphragm, but in a floor we'll just see that 1-point load. This one for a roof we'll see actually an area load, but we can also see an example of that coming up and when we build a model. Now, once we've applied that load, let's talk about the walls themselves. The load gets applied to the structure. Now you run the model. You have some choices to make. We have 3 types of walls you can design. The very first type there is the segmented wall design. That meant that what we're talking about here is really just the segments. What we call here is more design regions. So if we look at here, this kind of strip or segment is what we meant in this hatch right here. So that segment is what we're going to be resisting that shear load. So as you apply a load to a wall, that V is your shear, and each segment is going to be designed separately, as if that opening area has an ineffective section between it on the top and bottom of it. So each, we see if we had just a wall without openings, it would always be considered just a segmented wall. If it has openings, we have a couple other choices, but the first choice would be still calling it segmented, and each full height region here, so any region that you consider from going from the bottom of the wall to the top of the wall, that can be considered a segment. One of the things when you do segmented design, you'll note you get hold downs at the bottom of each segment. So you'll see that I have hold down listed on each side of that cord. The cord is going to be the outside element, so the cord is going to be, you're going to have a cord on each side of your segment, and underneath each cord you'll have a hold down. So when you design it as segmented, you're going to get these internal hold downs. Now, the next option we have is going to be perforated, and this is going to be a little bit more, theory-based, not very. So the segmented, what's nice about segmented is we're designing that based on each segment region, and we get all the forces inside of each region, and we design that separately, each region. Now, in perforated, you take it more as an envelope of the wall, outside perimeter of the wall. We think about this as, this is kind of more basically goes back to the hand calc theories of how things work in the NDS. You look at it and you say, what is the entire wall? What is the length of each segment that is full height? Subtract out the segments that have some openings in it, and then we just kind of basically design it like we collapse that section. It's not there, and we have hold downs on each side of the edges of the wall. And we design for L1 plus L2. We just ignore that inner opening area. L sub 0 looks like right in my picture here. So when you're perforated, it's a nice hand calc method, and you can really get back to that using your NDS calcs. And we show you that all in the detail report. It's kind of a nice way to see it, but it's a little bit more based on the theory versus on what's happening on each strip or segment, what we call that. So we've got that perforated wall method design, and then the last one is the force transfer around openings, which is sort of a blend of the two. What's happening in here is that we take that wall, we take that opening, and around each opening we break that into little sections or segments. And what we have here is 8 segments around those openings. And we're going to basically cut across each one of those segments and find the forces of what happens in each segment. And then what we're going to do is we're going to design for the worst case, so the entire wall gets designed for that worst case segment. And then we also give you those forces across that opening, so you can tie that. This force transfer around that opening is what you're going to be putting straps in there to design that, and we're going to give you the actual FEA forces that are happening at that across that span right there, where we're tying that opening together. So again, force transfer around openings, or FTAO as we shorten it. It's kind of easier to say there. But this also gets hold downs at each side of the wall. So you get to do some of the things where you saw in the perforated method. You're going to use the outside edges. You're designing for the entire wall based on one of those maximum that we're going to find there. And each segment gets broken up into these little 8 segments, and we can see that in the opening report. Each opening report is going to give us a lot more information on what's happening in there. Now, this is probably the most technical and probably the hardest to do by hand. So if you are using FTAO, it's really a nice tool to be using that inside of RISA 3D, and RISA we'll see inside of RISA 3D when we get to the lateral design. So internally, just to give you a side note, and we can see some of this when we design that wall, but what is a wall element? I just want to refresh your memory on going back to the finite element analysis. What's happening there is we're building this plate mesh internally. So we've got a mesh of plates going on behind the scenes, and you can see kind of from this top, you see all that sub-mesh of plates and built in there. Now, if you were to do this by hand, it would be really kind of a difficult and tedious process. And we used to teach folks how to do this all by hand, and you can do that. But what's nice about the wall is this is all internal for you. So you can just drop in openings and drop in your wall panel. It automatically will mesh this opening for you. So when you apply that load, the loads are going to go and distribute inside, and you'll see the forces in these plate elements as contours, but you don't really have to do much past that. You're not going to you can visually see it, which is a really great confirmation of what's happening and how the forces are flowing through your walls. You can see some of you get an actual increment here. It tells us what is happening in that wall. So this is a nice confirmation, but you don't really need to go into that manually and pull out these forces and design for that. A lot of that's being done for you after the fact. So we get to see all that, but all the hard work is taken out. Hopefully you just get to take the benefits out of seeing it graphically on your screen as a contour. So let's go ahead and build a model and see how this works in practice, and kind of work with all the different elements I've showed you and kind of reiterate some of those topics. So let's go into RISAFloor. So if we start a model in RISAFloor, we get just starting a model. I'm going to be able to create a new floor plan just by clicking on that. And I tell the program I want an original floor, and I'm going to say this one's going to be at 12 feet elevation. We'll kind of leave a lot of this out, but we'll come back to all the defaults that we have, and I'm just going to kind of start off. Now, in RISAFloor, what we're looking at, if you're not familiar with RISAFloor, is we're looking at a floor plan. So we're going to be telling the program, looking down on plan view, we want to start drawing our model. And typically, we would use our grids. We could even import using Revit. What I want to show you guys is a feature that's a newer feature. We could always import through DXF, and you can say import a DXF file, and we can import the entire file floor by floor, and it will let us pick a file and import that. But we also have another tool. So if you imported it floor by floor, You could have had drawn your model in maybe Autodesk, AutoCAD, drawn it out specifically, and then bringing it in. But if you have a large-scale model with a lot going on, you can also, I just sort of drew a simple AutoCAD model here, but I just sort of laid out what I wanted here in AutoCAD. It was really easy to draw in AutoCAD, and I want to just bring that in and be able to trace on top of this. Now this is really great also if you have architectural plans and you want to just draw the structural underneath on top of it, you can do that as well. Now the way we can import that AutoCAD is by going over to our drawing grid, and we click on the drawing grid and we say import DXF. And so usually you have just a standard grid here. What I want is that third option, import DXF. And I tell the program where to put this, the drawing grid origin. I'll just tell it to be at 0. That's fine. I can tell the scale factor and any units I want to convert, maybe just going from inches to feet, or however I want to lay that out. I can tell the program that the plane I want to be on, I'm just going to say it's the XY, and I'm going to browse for my file. So I'm going to pick out a file I created, which is, I just showed you that file, say open, and I can tell the program here to do any kind of coloring or whatever I want the colors to be. I can select those colors for those backgrounds. I'm just going to use my gray and tell it to bring all of my layers across. So once I say done, I see that I have a DXF outline. Now this is just a background. So it's not actually like bringing the walls in. If you wanted to do that, you use that file import DXF. This is just my background. So I can draw on top of this background. And I can do that, the way I did that was just by using my import DXF tool. It's a little different. Now once I have this background in, I'm going to start drawing some of my walls. Let's talk about the walls, and before we start drawing them, let's go and look at what their definitions are. So on your data entry toolbar, which is on my right side of my screen here, I have my data entry toolbar. I typically always kind of want to walk down this list of items. My wall design rules is right there. I pop that open, and I can tell the program here what my unity check should be, and then I start to worry about what type of material. So I have concrete. I'm not going to be doing concrete in this model, masonry, but I'm going to be worried about the wood walls. So starting on this tab here called wood wall studs, I can call this wood wall studs here, label anything I want. We'll just call this my 6-inch wall. And I tell the program specifically what size wall I want to use. So my top plate, what size should it be? I'm going to stick with a 2x6 wall. So I'll let the top plate be 2 2x6s. The sill plate will be more than 2x6. If I needed to change these, I obviously want to stay with a 6-inch across there, or an 8-inch, or however I want to be consistent. But if I did need to adjust that, I could just pop in here and pick a different one from that list. So I'm going to say 2x6s will be what I'll stick with. The minimum stud size, I'm going to tell the program 16 inches is my minimum. My maximum stud size, I'm going to go all the way up to 24-inch spacing. This is spacing. So I'm going to tell the program you can go from a minimum stud spacing there of 16 to a maximum stud spacing of 24. So I'm going to bounce between 16 and 24, and then you can choose to have it be green lumber. I'm going to leave that unchecked. I can also change my header size and the header material if I wanted the material of the header to be different than the material of the wall. So laying out just my 6-inch wall, it kind of lays out all of the different information. I can jump over to the wood wall fasteners, and that's the second tab, actually the last tab here. And this one lays out really the design here of this wall. So the studs is going to be the first thing, but the fasteners is what we really mean by what's going to be here for the schedule or the thickness of that panel. So when we click on the schedule, we can open up a database of different information here. Now, what we see is I have a whole list of IBC 2006-09. It's basically the same thing as 2012, so we haven't changed that name for you there. But what you do see is that you have a long list of different size panels. And the information on that label should tell you everything you need to know, whether it's structural grade, 5 16-inch thickness, 6 penny nails at 6 inches. That's pretty much the name gives you everything you need to know about what that panel is. The 2 in parentheses tells us if it's double-sided. You've got all sorts of information listed here. Now, you can see as you scroll across there, the information that you get here this is all coming in from outside of the program. So this is from Excel. You can go ahead and add to this list if these were something that you needed to add, maybe a proprietary type of information. Otherwise, typically this is just the IBC information. You can see the shear capacity is listed at that end of that number. That's really the hot number that I care about. The GA also helps us information for the deflection, but we can see here we've got our shear capacity listed. It is the most important piece. So you've got listed here, I'm just going to pick the whole panel group, but if you wanted to narrow it down, you could also tell the program, hey, I don't ever really want to, I know I want to use 7/16 on this, so just tell the program, use this entire 7/16 inch grouping, and that's what we'll be using for the model. But I'm going to tell the program here, I'll just use the whole database. Find whatever works within this database. And so I can say OK, and it leaves it as that database. I can also narrow down the size of the panel, the thickness of that panel, based on minimum and maximum panel size here. So maybe I wanted to choose the entire database, but I can narrow down the thicknesses over here as well. I can choose if I want it double-sided or not. I can tell the program, use just whatever is optimum. Otherwise, we can say yes or no on that. And I can go ahead also and do maximum and minimum nail spacing here. So we can go ahead and tell the program what the maximum and minimum nail spacing I want to be. The hold down chords, those are important there. We want to know what are we going to be using for our hold downs. Are we going to be using 2 2x6s? Probably, because that's what the size of our studs are. They were 2x6s here. So for the hold downs on each side there, their chords, they're going to be attaching to 2 2x6s. Now the hold downs have a hold database as well. So if we open up the hold down database, I can see a list here. We have just some default ones. Probably HDU is probably the most popular. So let's switch ours to HDU, and I can see I have a laundry list of different HDU Simpson hold downs. You can add to this list. You can modify this list. Again, this is sitting outside of our program in an Excel spreadsheet. So if you have a different manufacturer you want to add to that, you can. You can also change some of these values as you need. These are values that often get changed throughout the years, so we can adjust that. But we can see here, let's just pick the HDU, and I'm going to say OK. And we'll see that is going to be using that whole database of HDU. So I've got, this is kind of my definition laying out for both the studs and the fasteners is what we're calling these. The hold down and the thickness of that panel is what we call the fastener schedules over here. So what I'll do is I'm going to close that down. I could add different walls, several other walls. You just push enter to create a whole laundry list of walls. Typically, you probably would want interior walls maybe differently than exterior walls. I'm going to keep them all sort of using that one first top. I want a 6-inch wall there. But what you could do is you could add to that list. I'm going to start drawing these walls. Let's get some walls in the model. So I'm going to click on Draw to Modify Walls, and I can tell the program here to choose a wood wall. We'll tell it to be a Doug fir material set, and that to be the 6 inches. And I'm going to choose to be lateral. So when I'm drawing walls, I'm just going to be drawing it around there. Let's see, this is rendered. I'm going to just turn it. You'll notice when I draw these walls, they are red. Red versus blue indicates that they're lateral walls. And I'm just drawing these around the perimeter of my building. You can choose to draw these walls here as full segments across large spans, or you can choose to draw them into little segments as I'm doing just point to point. Now, what I always ask myself is how are you going to be wanting to design them? Are you designing them as one giant wall across here? So this is a huge hold down on each edge, or do I want to put hold downs kind of at these intersections? And in my model, I'm just going to be doing them more like they're components built, separately as wall panels. But you could do them, fully across this entire back wall. You could have drawn that continuously across. You have to answer that question based on how you want your design. So I'm almost done, but you'll notice on this DXF underlay, what I can do is I can click to intersections. I could, if I have other elements crossing that, I could have clicked to that. The DXF makes it really handy, and it's just so easy to lay out a DXF quickly, and most people are pros at drawing in AutoCAD, things like that real fast. So if you do that over there, you can easily underlay it, and it makes it really helpful. Now, I'm just drawing in all of these walls. Now, what these walls represent for me are, these walls are going to be basically my lateral system. So I'm kind of just outlining what's happening on this lateral system. And what you'll see is that I have some gaps in here. I'm going to just put some beams or collector elements in for these gap hallway elements that I have here. So I've laid out all of the walls that I want to put in. Oops, and it looks like I just neglected one little wall here. So what I want to show you here, actually, I didn't take this wall all the way across. That's okay. This little segment may be too short for design, but we'll try it and we'll see if that actually was a little short for design. It will give us a reason why we might want to draw that as a full length versus a little segment like that. The code has some restrictions when walls are too short for that they cannot resist any lateral load. So that might be a good example of that, but we'll see how that works out. So once you have your walls drawn, you can double click on a wall and we can see that wall panel editor. It shows us the wall as it's drawn. You can see here, if we can just measure this wall here, kind of using my F5 key, I can measure that wall and I see that it's 30 feet in distance across. As I scroll on that wall, now I'm going to have to see on the right corner here, you'll notice on the right corner of my screen, all the way at the bottom, when I scroll over that wall, I see dimensions. And that's where it helps me to see to draw things in. I could also use my grid here, my grid increments to help lay out this. This wall grid increment is coming in at half foot right now. If I wanted to, I could tell the program, hey, give me a grid of 1 foot increments, and that might be a little easier for me to see every 1 foot versus every half foot, and I can draw on there, or I can actually specifically lay out this grid to help me draw in my openings. So I'm going to draw just a couple openings representing what's happening in this model, and you'll see here, actually I got a little big here. I'm going to do it one more time and just draw an opening in. And once you draw that opening in, you'll notice a header pops right onto the top of that opening, and I can create regions just around that. Now, if I didn't push that region button, not to worry, it would have done it for me once I pushed solution. It would have drawn these regions in. And these regions, what we call these drawing regions here, are just like I mentioned, those segments. Regions or segments are very similar items, and what they are, they're full height. These full height R1 and R4, those are segments that can be used for design, and these R2 and R3 will be neglected if we're in a segmented. If we're perforated, we're just going to do that, a similar type of theory where we're going to just count whatever the distance here, the span across R1 and R4 and sum them and then design that. So we're going to see we have kind of different options once we look at solution, but all of that is based on whether I choose design method, segmented, perforated, or force transfer around openings. If you don't have any openings, then it's going to be a segmented wall. If you do have openings, you can make some choices here. So let's first of all, this first wall, we'll use it as segmented. The second wall, let's double click on this skewed one and draw in an opening in here, and let's create this one as perforated. And I'm going to say okay, and the next one I'm going to do is force transfer around openings. So we'll have 3 examples for us to work with, and we can kind of think about how those will work. I'm going to drop a couple more openings. Those are sort of window openings. We'll drop in some door openings, and this is just a nice example for you guys to see how the openings are going to be treated in our models. So I'm considering this front wall to be really our, the street side of the building, where it would have really large openings like this, and then you could obviously go ahead and make the other openings along anywhere you need. But this is just for a nice example. So once I have those openings, this is a 3-dimensional model. You can always go to full model view and take a quick look at how those walls laid out. You can rotate it and see what's going on in that full model view. But what I'm going to go pop back into is just this plan view. I'm going to draw in those beam elements now. Now we've added some cool enhancements to the databases, and I want to show you guys what we've always had here is if you go to materials database, and you open up that spreadsheet, you can see the wood, and we've got a couple changes. You've always kind of been able to look at the wood species over here in the wood spreadsheet. Take a look at the Doug fir, southern pine, and see some of the glulams we have. It looks a little bit different than it used to. We have some different options here. When you say type, the program is going to ask you what kind that is. Is it solid sawn, glulam, SCL, or custom? You can see if you choose different types of things. Let's create a new one just by pushing enter. You can see you could choose SCL from this list, and you have a laundry list of different structural composite lumber options here. You can also do change that to be maybe custom, and that would work off of what we have, our custom database. So here we see custom wood species database. So this is kind of how it's typically worked in the past. It's a little different layout. But what we've also done is we've enhanced this a little bit further by going up in here. This is our shape database. There's an icon that looks like a wide flange. If you click that, what you'll notice is it's kind of similar to when you're using any hot rolled steel. You can go through all the database of shapes for hot rolled. Wood has been enhanced to change so that we can see a lot of the information just like we would see in any of the other materials. So if we choose, for example, a Doug fir, we can choose a 2x6, and we can then see what its design properties are. So if we look at this, we can see Doug fir, we see a 2x6, and then we get to see what those design properties are directly before we run the model. This has been a request from a lot of folks wanting to know, hey, I want to see exactly what's happening in those properties before I run the model, and then I can base the judgment on what beam sizes to select before results. The other thing to note is that these values actually change based on the size of that. So if you'll note, I don't know if I have a good example here, but some of these values will change if it's a 2x4, or if it's a 2x6, or if it's a 2x12. These values will change, and it's really helpful to see that. You can see the glue lam properties and see what those glue lam properties are listed right here. So a 2x12, if I give it a glue lam 2x12, what are the properties listed here? And we see some of all that information listed out for us. The other thing you can do is you can create a new material right off the bat straight from this dialog. Just by clicking on this little 3-dot button, I can create my new custom SCL, and I tell the program this is a custom SCL, and I can give it create a new custom material directly in here, or I can choose an SCL from the type here, and I'm going to give it a property of some large species properties here, 2.0E, and I can go ahead and tell the program I'm going to be using this SCL APA. But you have all the different manufacturers listed here as well, and already in there for you. So I'm going to say OK, and I'm going to use this custom wood species for some of my modeling. I can also change the plies and do all sorts of different information listed here. So it's kind of a nice thing to be able to see directly in this database. Now if you didn't see, I just popped in there using this Edit Shape database, and that's where we went in and we popped over to the Wood tab. This is brand new in a feature here in our latest version. So what I'm going to do is I'm going to start drawing some of these beams. We've kind of talked about those beams. I'm going to draw some of these beams on our model. So I'm going to say draw or modify beams. I'm going to go to the Wood tab, and I click on that wood. And so for my glue, I'm going to choose glue lam as my beams, my lateral beams I'm drawing across. To close off this is my collector elements, and I'm going to say apply, and I just sort of draw that across to close out this hallway area. Oops. And we'll just draw that across, and it goes right into those empty spaces that I needed some beams there. Now the last piece I want to do is draw some of my gravity infill framing. So I'm going to click on Generate Beams within a bay, and I'm going to tell the program that I want to use, first of all, I'm going to use some of my I-joists. I also have an I-joist database. I'm going to tell the program here to use the APA I-joist, but you can pick from a list of different types of I-joists we have. I'm going to say APA I-joist there. And I'm going to tell the program that I want the spacing to be 2 feet, not to exceed 2 feet, and to apply it horizontally. So I can circle this entire top area and the entire lower bottom area, and I'm going to frame it in the horizontal direction and for these areas. For the hallway, I'm going to go vertically. So I'm going to change that. I'm going to go back to that. Probably not I-joist because it's a pretty short span. So I'll go pop back into the wood type of format and maybe just be a Doug fir. That should be fine for that span. Again, the same type of 2 feet would be okay, but it's going to go vertical in direction, and I could just click on that. So I can lay out, now my whole structure's got all beams. Gravity beams are blue. They're indicated in blue. That's why they're showing here all my gravity beams are a different color. And those red beams are lateral, or they're going to be my collector elements as I go over into RISA 3D. What I do now is I need to put a edge, we call a diaphragm edge around the entire structure, so the program knows where to attribute those loads. So I'm going to go ahead and use this diaphragm perimeter. And I have a choice here. Am I going to be using a flexible or a rigid diaphragm? So first off, let's start with just a flexible diaphragm around the entire edge. And I tell the program, just draw it 4 inches from the center line of the edge element, which is just our wall, and it pops out there. So I can see I have a little bit of perimeter there all the way around the edge of the building. Now, the program has some defaults, and I skipped that in the beginning, but the defaults here are telling us that this is going to be at a 12-foot elevation, and that it's going to be using a wood deck across that, and that deck is going to be spanning 90 degrees. So the deck information comes off our deck definitions. If I click on the data entry toolbar, there's a deck definitions, and there's a database here listed as wood deck. You can see if we open that database up here, it tells us we can change that deck thickness. Maybe it'll just make it 1 inch, and it will base itself off that wood density, and it's going to calculate its self-weight based on that 1 inch thickness. I can tell the program what the unbraced length of that is, what the maximum span is going to be, and so it's going to give me a warning if I went beyond 4 feet. A plywood probably typically won't be spanning more than 4 feet, so that's a good number just to give me a warning if I did any directional problems. The loads, I can tell the program here, it's calculating its self-weight for me. If I have any superimposed dead loads, so any loads that are going to be above and beyond that dead load, I can put that there for more of its deck materials. Maybe there's sheething that is attached to that deck and I want it to be above and beyond what I have as self-weight. Any construction or dead and live loads I can put in here. So I've got that all listed as my wood deck default. It is spanning right now 90 degrees based on the horizontal. So that means it's vertically spanning on my screen. That works for most of my model, but it does not work for this mid-span area. So for load attribution, I need these hallway beams to be loaded horizontally. So in the program, I don't need to do anything for the most of the beams that are going in the night, that the span goes in across my screen and that the deck spans vertically. But for just that one area where I want to override the default, I tell the program here that I would like to override your default. I'm going to go to the plan horizontal, and I'm going to tell the program to go wood, and I can select that there, and I can just tell the program, hey, go span that horizontally. I can display this with the default behind it, so I see that vertically on the top portion, I choose horizontally in this middle section, and the load is going to be attributed based on that direction. So now, when I have all my deck in place, let's put some load on that center area. First of all, there's some default loads, and the default loads that we tell the program here is going to be what we call an office loading. It's just a typical load that we have defaulted in the program. So if I go to area loads, I see that in the area load default, office has a DL of 10 pounds per square foot, or 0.01 kips per square foot. It's got 20 pounds per square foot for live load. And then that is a reducible live load, so the program is going to know if it has enough to reduce that live load, it will. A tributary area, it will reduce that for us. Vibration loads are going to apply to steel, so we're going to ignore that one. And then dynamic loading is going to be the dynamic loading above and beyond the self-weight. So that means that we want anything that we want to add to the dynamic mass. So typically that's going to be just your same load as what you have for your dead load. But sometimes maybe you've added too much dynamic mass into this dead load to account for, I don't know, things that are going to be maybe office furniture, or things that might not be really part of the dynamic mass. You want to dial that number, that dynamic load, into a different number. Or maybe this is not enough. You need to add more to the mass. You can attribute more to that dynamic mass. So what this is accounting for is superimposed dead load above and beyond the self-weight of the beams and the deck itself, and what we calculate for the seismic calculations. So we've got all that laid out. We also have a public load, and the public load there, I'm going to put in that hallway. It's a little bit higher there. It's going to be the same dead load, but it has 100 pounds per square foot for the live load. So what we'll do there is we're going to draw in an area loading on top, and it's going to replace the area load that was below it. The reason why I know that it's replacing it is because the additive checkbox is not turned on. If it was additive, it would add to it. Otherwise, it's going to replace that load. So I'm going to go ahead into the draw area loads and choose public. And I'm going to tell the program here I'm going to box a perimeter, and I'm going to zoom in a little bit. Let's turn off this decking, okay? And I'm going to zoom in a little bit, and I'm going to put some public load on top of that. So I've got loading in here. I see the loads applied, and I'm going to go ahead and also, I'm going to just take a quick look at this in 3 dimensions. So I can see here I've got my full 3-dimensional model. I've got beams. I've got walls all in place, and I'm popped back into my full model view. and I can now start applying other floor levels. So I'm going to insert floor, and I'm going to copy that floor, and let's just copy everything about that floor. This floor is going to be going up the building. We'll tell the program here we're going to go up to 24 feet, not 34, 24. And we're going to say that's going to be all the same information, but just 24 feet high. And we create a new floor. And we're also going to, let's create a new floor one more time. We'll go copy that floor, and that one's going to be at 36 feet, and everything will be similar. Now we have a 3-story building in place, and let's take a quick look at that full model view, and we see that this is now a 3-story building. Let's toggle it back here. And we see that that's a 3-story building instead of our single story. Everything got carried with it. Those window openings, everything is there for us. It's just three levels. The last level we want to do is that roof level. So I'm going to go ahead and go into my roof level, and I'm going to go into insert floor. One second as I stop rotating this slowly. I go into insert floor. And this time, everything is the same here. We're going to say this is, but we'll call this a roof, just change the title. So we remind ourselves what that is, and we'll put that at 48 feet, and we'll say okay. All right, so now looking at this roof level, what I want to do is change some of the framing. This framing is not going to quite work for our roof level. So what I'm going to do is delete the roof, all that gravity beams. So I'm going to use my selection tool. On the left side here, I have a select criteria. I can select or unselect the beams that have a function called gravity. And so if I choose function gravity and unselect, I say apply and OK, I see that they now are unselected on my screen. I'm going to use my reverse or inverse tool and select only my gravity beams. Now I can delete them all at the same time. So I say delete based on this criteria and delete them, all of them, the selected beams. Now they're gone. Now I still have all those awesome collector elements. I didn't delete that. I don't have to draw them back in, but I just deleted all the gravity ones. That's it. So now I can redraw. I can say let's draw this again. Let's use our infill beams. Let's make sure that these are glue lambs. We'll use them as glue lamb shapes here. We'll choose them to be glue lamb, and then we're going to say they're going to be vertical. Instead of horizontal, they're going in as vertical, and then they're going to be an equal. Let's say these are going to be a little bit tighter spacing, and we're going to apply these in as vertical elements there. There we go. So we see that they all apply directly to our structure. What I want to do here is I want to apply these. I want to apply a slope to this. So I'm going to go ahead and I'm going to use my slope tool to do that. So I unselect the entire model, and I select a portion of that model. And let's see, I'm going to go use my sloping tool, which is right up here. It looks like a sloping icon. And I tell the program here, I want to use this as 4 on 12. And I want to tell the program here that I'm going to be sloping. It's asking me for 2 reference points to define the base plane of the roof. So I'm going to choose that outermost points here. I can choose any points. First point just starts that plane, and the second point here defines the plane. So what's happening is that the program is vertically, from that point upward, it's going to be sloping 4 on 12. If we look at this in isometric view, I can see I sloped 4 on 12. Everything attached to it sloped up, but whoops, not the back side of the building, right? So we need to slope that portion to meet this front portion of the building. So what we'll use is we're going to go back to our plan view, and we're going to unselect everything, select that back portion of the building, okay, and then we're going to do a sloping. The back portion we'll say is maybe 4 1/4 on 12 because it's a little bit of a different span back there, and we will span that back portion up. And if we look at this in isometric view, we now have a nice sloping backside and front side. So we've got everything kind of laid out in the structure. We can go back to our full model, and we see here the entire structure is laid out. I'm going to go ahead and run this model, and as we run it, it's calculating the loads down the building. And so we're counting all of the gravity loads per floor level. So everything is going one by one, counting all the walls. If we had columns in this beam or posts, we would be counting all those post loads straight down the structure and doing all of that gravity design. So mostly here in RISAFloor, what I'm concerned with is all of these gravity beams. The lateral beams are going to be designed here as well, but they're also going to be taken over to RISA 3D, and their main purpose there is going to be seeing other loads for the lateral. They'll also be checked for gravity when you're over there, so you'll get kind of the both sides of it over in RISA 3D, but what you're doing over here is concerned with what those beams are being concerned for gravity. So looks like I forgot these deck exceeds span. That's a nice warning to me that I did not address my span on the top of the structure. So we'll skip past that for right this second, and we'll take another look here. But what that was mentioning to us here is that I forgot to address the direction of the deck here on the top. I'm right now showing that I have the deck spanning in a direction which is opposing where I need it to be. It's going vertically, so it probably doesn't want to span that way. We want the loads to span horizontally so that these intermediate beams, all of my gravity beams, get loaded. Well, let's go back to the lower level and review some of the results. So in RISAFloor, we can take a look at maybe one of our beam results here, an I-joist, for example. We have a detail report, which gets to show us a lot of information about the structure. We see the dead load and the live load in here. We get to see all of the loading, the shear and the moment diagram, the deflection. If there was any axial load, we'd see that. We get to see code check. So it tells us here that there's an envelope solution, and what that is all the loading breakdown. The code check is listed below here. We get to see the bending and the shear calculations for this one. You can always notice, I always like to see this stuff because I get to see what's the percentage and how well is it doing. It's 32% deflection capacity. The shear is 42%. Bending is 38. So it's, usually a lot of times you end up seeing actually deflection sometimes controlling. We get a little note telling us those connections are not designed. So for I-joist, you're going to be doing the connections outside of the program. But for typical beam structure here, let's look at glue lambs. This is a nice way to see here all of the girder, if this would be acting more as a girder type of loading here, where we see all the beams framing into it and all the point loads that creates. And as we scroll down below that, we see what the capacity is here in listing the bending, if there's any of the factors listed out, and the deflection criteria listed here. So we're seeing how well it's doing. So that's all your beam, and you get a nice layout telling you the design results. We can see here specifically what was happening here with your design results. It tells us the size of the members that were designed. We get to see the code check. We have a spreadsheet listing the code check. I love the detail report because it gives me the pictures and the graphics, but when you're looking at a whole structure, it is helpful just to see that as a kind of a one-off, what's going on quickly in the structure. It tells us what the code checks were and how, the governing load combination, the locations, things like that. So it's nice to see that for a full building. You can have all of those spreadsheets give you a nice breakdown per different types of things. Now, what I also want to see here is the wall results. So if I click on the wall, oops, I'm going to zoom in a little bit to click closer on the wall. The wall results here in RISAFloor are pretty simple. They're just going to be your gravity. So all I'm really counting is vertical load down the structure here in RISA 3D. So if we look at a segment, all I have is axial. That's all I care about, and I design the studs based on those axial loads. So not a ton to look at over in here in RISAFloor. Once we get to RISA 3D, the real interesting part of that gets designed. So I'm going to, on the basis of time here, I'm just going to jump over to RISA 3D quickly so we can get some of that loading here for us and kind of work on that. So I'm going to go over to RISA 3D. Okay, so in RISA 3D, what we did, we just took only the lateral elements, just those wood walls, the red elements, and we tell the program here we're going to be calculating the wind and seismic here. So there's a calculator. These are automatically calculating it for us. We tell the program 120 miles per hour, exposure category C. I can say calculate those loads. And what I see in here is this breaks down kind of the echoes of all the information I just put in. It tells me some of the design parameters based on what I put into the program. And lastly, that QH there is going to be our kips per square foot. So we're seeing all that listed right there. That's kind of the big number that gets calculated in there, and it goes per floor level. Now, as I mentioned, you can take the program and tell the program you're going to be using a flexible or a rigid diaphragm, but no matter what, you're going to get 1 point load in the X and the Z direction, and we're going to transfer that into the structure. So we'll see here that we have the slope roof gets a portion of that, the rest of the structure gets a portion of those loads in the X and the Z direction, and we can see it graphically. So if I'm designing the structure, I would typically print this spreadsheet and have this for my design calculations. And go from there into RISA 3D. And then I will also go into the seismic loads and I'll put them in the program here specifically what I want for my seismic loads. So you can tell the program an R value, maybe 6.5 would be a typical R here for our wood walls. We can tell the program per the location we're at what our SD1 and SDS are. I already have some defaults set up in here, so I have my SD1, SDS, and S1 listed here, and then it will calculate those loads for us. Now, in seismic, it does very similar. It breaks it down. It echoes the report of what you gave it. It tells you exactly what those calculations were. The base shear is listed right here, that VX and the VZ at 47 kips. So it's pretty small for our structure. Probably we're going to have a lot larger in the wind than we are going to have seismic. We see our actual forces in the X direction and the Z direction are smaller here in the seismic. So wood's going to be typically probably designed both on the wind, maybe because it's not so heavy. If you have some other type of loads in your structure, maybe you get a heavier loads there, your weight of your structure. But what I always also like to do is do a back of the envelope check on myself, on my hand calcs is, hey, does that weight of that structure jive with what I think it should be? If that does not, then all of these calculations to follow are not going to be right. So I might want to go back to RISAFloor and make sure I modeled that properly and I put the superimposed dead load, or what we call that dyne load, properly. Otherwise, I might not get the right forces in the X and the Z direction. So this is kind of why I like to use this weight column as a sanity check of, yep, that looks about what I would expect that floor to weight to be, and then we go from there. So I can see here this total shear, and it gives me the total weight of the structure. Another really good total here is the total weight of the entire structure. Does that jive with what you think it should be? Otherwise, it might not be. You might not be modeling it correctly. You have to go back and take a look. So I'm going to say OK. I would probably have printed that had I been designing the structure. What you'll notice is only the wall elements come across, and those collector elements. The other parts of the structure are gone. Now, they're still back in RISAFloor. Don't worry, we didn't lose them. And what's great about it is that actually whatever they were contributing to the structure is still there. So we had point loads from beam elements. We had all sorts of dead loads coming down. That was on the structure. All of that I'm displaying right now is still on the elements. So we're still seeing those dead loads being attributed to the elements that we're designing currently. We're just not having to bog our model down with a lot of extra elements. And you can see as the structure gets 3D, it can get pretty complicated. So what I suggest you do is kind of use some of your tools on the left side, your selection tools, to help modify things and take a look at only things that you want to see. For example, I'm going to unselect the entire model and just select the lowermost portion of this model. And I can turn off or unselect, lock out my view of that top structure using this lock button. Once I lock that out, I can look at this in isometric view, and I get to see the whole entire structure on my screen. This is so much easier now. I can do that floor by floor, pop from floor to floor to floor, seeing what's happening in the structure and verifying on each level. Otherwise, it can get a little complicated. So now let's take a look at those dead loads. Whoa, much easier to see. You can see how it's so much easier to see all those dead loads now. But you have a laundry list of loading. You have dead loads and live loads. Had I put any snow loads in RISAFloor, those would be there. Had I put any rain loads, those would be there. So all of my loading that came from RISAFloor is there. But what's also nice is that I have wind loads in the X direction calculated for me. If you look at the basic load cases spreadsheet, you can see all the loads came across for you automatically. So we see all those distributed loads on there. We also see that we have a spreadsheet for all of those wind loads in the X direction, wind loads in the Z direction. Just by clicking on that number 4, a spreadsheet pops open with 4 rows. That's what that 4 indicates, is that there's 4 items in that spreadsheet. And I can go to the Z direction and check those out. They're grayed out, these numbers. These numbers are for your reference. So you want to be able to see them. I want to know exactly the quantity, but it's not something I can modify. This isn't something I can modify. But what I could do, if this is numbers that I decide later on I want to do something different than these numbers, I could copy this spreadsheet and create my own custom one down below and just give it a different type of category. But this is here all for your reference. So you can flip through and go from one to the next and toggle your way through that different loading. Now, what I'm going to do in this model here is I'm going to see, I can see, zoom in a little bit, I can see that I've got wind loads in the X direction. That's a point load distributed to that wind load, into that whole diaphragm. This is a flexible diaphragm. If you remember, we said everything right now is going to be a flexible diaphragm. So let's go ahead and create some load combinations and run this model. So in the load combination spreadsheet, once you open that up, you'll see that there's an LC generator at the top of your screen. If you click on the LC generator, you can choose this is a gravity, wind, and seismic generator. So the gravity one is the first one we want to look at, and I can choose the code I want to be designing towards. I'm going to say 2012 IBC ASD design, and I can tell the program to generate that, and it's just generated my dead loads and live loads. Had I done any of these other special loadings, I would want to have included those combinations. I did not, so I'm not going to include that. But I pop over to the wind, and I can see I have ASD IBC 2012. I'm going to tell the program here I can use the X and Z with eccentric. I could even go with quartering. I'm going to just use eccentric, but quartering would help you get to that case 1, 2, and 3, 4 different types of quartering. We'll apply those loads in combination together. Eccentric should be fine for good enough for our analysis here. So I'm going to say generate those, and I'm generate the roof wind loads, and go from there. And I see, and the last one is the seismic. I'm going to pop over there. I'm going to also tell the program X and Z with eccentric. I can do all sorts of other things in seismic, reversible, include the vertical load component. I can say the redundancy. Anything you want to do in here, I can do all that for you. But I'm going to just say generate and say close. And now I have a list of different types of loading in here. So I have right now 39. You can get a lot more complex than that. But let's just quickly just look at one different loads combination. So here we'll just do a dead load, and we'll just combine that dead load with maybe just a wind load in the X direction. And we'll solve just a combination with just those two for now. So I solve that combination, and it runs through each of those different ones. Now, just because I don't have the whole model selected doesn't mean that it's not there. So when this is running through this analysis, behind the scenes, it's counting up all the loads and doing everything as if the whole model was there. This selection process I did with the locking, all that does is just locks it out of my view, so I don't have to see it. But not to worry that it's not there. It is still always there. So we can see it iterates through a combination of different things, or we're going through solving the solution. This is, as I mentioned from the very beginning, an FEA solution inside of those wall panels. So it's a pretty large model with a lot of walls, and each wall is getting broken into sub-mesh into plate elements. So sometimes you can notice that it will take a little while for you to run a model, and that's just due to the fact that you've got a lot going on in there. So what we get was a kind of a nice warning message telling us what's going on. First of all, remember I mentioned I did that little teeny wall in the front of the structure, and that one looks like it's telling us, hey, I cannot be designed because there's an aspect ratio problem, design not done. So, okay, that might be something we want to reconsider drawing that stubby wall. We might want to draw it longer so we get some design, or we just don't count that wall as part of our lateral load resisting, and it's there to resist the load because it is there, but it's not there for design. So it's up to you how you design that. Perforated walls cannot be sloped, so I have a perforated wall that I called perforated and it's sloped. I might want to switch that over to segmented so I get a design. And then it tells me another wall has got some aspect ratio issues. So those are some warning messages I'll probably want to pop back and address later on. But what I can see here, let's take a quick look at what happened in some of these walls. So if I look at first of all, let's look at the transient, how that load got applied. I have a wind load in the X direction, and if we look at my basic load cases spreadsheet, you'll notice that I have a couple of transient area loads that got generated for me. Those are those ones I mentioned earlier, and what that means is that we are now turning that point load I put in, that 63 kips, into a distributed load around the structure. So that got distributed right into our model. That X direction load, it's a flexible diaphragm, so any wall that has any component in the X direction got some load. So we'll see, zoom in a little closer, and we can see these two are actually slow. If we look let's look on this in the plan view, so we can see down on the structure. These two skewed walls, and on each side we have some skewed walls. They're seeing a little bit of load because they have some direction in the X direction there, slightly in the X direction. So they are seeing some of that load. Not a lot less than a lot of the neighboring walls, but they are seeing some because they have some area that is going to be exposed in that X direction. So you'll see, but you have all the other walls are basing themselves on their tributary area. And you can kind of see how that looks like that. You see the different values here as they distribute across. The edge walls have less tributary area. The interior, this one's got a lot of tributary area, so we're going to see a little bit more load on that one. This one has a little bit more tributary, but we start to see this one has both sides of that. So it's basically working through and defining how much tributary area is it seeing in the X direction on that level. Each level gets this much load. So if I unlock this model and we look at the entire structure, we see each level has loads distributed on it based on this flexible diaphragm theory. Now if I pop to the top of the structure, let's go ahead and only select the very top of my structure, or the roof level, and look at that here. And let's see, I'm going to make sure I grab the right thing here. So I'm going to go ahead and use my selection tools and select the whole wall structure up there. And look at this in isometric view. And what I see in here is at these wall levels where that hits, I get those loads applied to the wall. But I also get that what I mentioned here is that roof level load. So I'm going to get that uplift. And what happened here is that there is a automatic roof load that got applied as you can see here, as a area load, and that's applied to this structure as an uplift on this side. And that converted right into a distributed load along the edge or the perimeter of that wall, or that envelope of that upper structure. So that loading got distributed there. Now, I'll show you guys, and after we see some design here, I'm going to turn it into rigid so we can just kind of see the difference between a rigid diaphragm and what a flexible diaphragm will do for you. But I'm going to look here in this isometric view, and let's go ahead and take a look at some of the different types of loading, of design we have for this walls. So we'll go back to the front of the structure. And I'm going to click on a wall, maybe a lower wall here, and I click on this wall panel 1, this 19, excuse me, and I see this is a segmented design. First off the bat, I can read it says segmented. I also know it's segmented because I have hold downs at each side of each segment, and so I see that each wall region or segment, R1 and R4, if you remember this is one we drew from the very first one, we'll see that each one is being designed individually. So we have this R1 and R4. We see it listed in our in this detail report. It tells us what the panel was designed for, what its shear unity check was, if it had any requirements for hold downs. This actually doesn't even require it. It's not very, looks like we're not seeing much load in there. We see that we can run, it tells us all the height to width ratio for that region. It gives us all the information on the studs, and then it gives us deflection. Deflection is based on what we see here is the maximum deflection is R4, this one right here, and it gives us what the deflection is. It tells us it's 0.056, and then it also tells us what the finite element analysis gave us. So we have two types of deflections. One's based on the calculation, and one's based on the finite element analysis. And we can sort of see that they are slightly different. You can sort of use this adjustment factor to help get these closer together. So you fine-tune how stiff that wall element is. Let's take a look at the region report. So what the region report is region 1 and region 4. Region 2 and region 3 are above and below those openings, so we don't see much happening there. But region 1 and region 4 gives us a summary of what's happening in plane. It tells us the axial loads. It gives us a breakdown of what the shear in the moment is. It also kind of breaks down here on the right side what that unity check is. So the chord force is the maximum and the governing chord forces, and then what its unity check is there. It also gives us the shear panel unity check, and it gives us all that information provided based on what the demand is listed here in this moment and shear diagrams. So you see all that information, and we see the panel that was selected and the capacity of that panel and how that 0.02 capacity meets the requirement of what we actually need in this wall, which is a low loaded wall here, so we're not seeing much. But if we go below here, we then see kind of a nice schematic of it. We see what that panel is. It's a 3/8 inch panel. We see the chord forces where it's seeing compression on both sides here. So there really is no tension on this panel. That's why we're not really requiring a hold down. It's heavy enough of a structure that this actually doesn't require me to have a tension hold down requirement. So you can see how that works, and you can see each side of that region and how that works in the segment. You also get opening report. In the opening report we're going to get is going to be used for we want to use the opening for perforated or force transfer and openings. We don't get an opening report because we're not designing R2 and R3 in the segmented one. So we want to be able to, if we want to use the opening design, we're going to change that to perforated. So let's pop over to the perforated wall. We've got the second wall I did here was perforated. It's slightly different. You'll notice that we don't even have a region report because the regions themselves are not being designed individually in a perforated wall. In a perforated wall, we're taking, well, you can see a lot of those numbers we're taking here listed out. What is the full height sheath? What's the length of the full height sheath? And it's 13 feet. Of that is going to be the length of the total length of the wall is 21 feet. The full height of the sheath is 13 feet. The percent sheath is 62%. And all these calculations, pretty quick, hand calc type things, get factored into what is the total unit shear and what is the total shear being applied into this wall, and then we get a ratio of what's going to be which panel gets selected for this actual wall here. So it's a nice hand calc method. You can see all the factors you need to do that hand calc method are here. You have your CO and your AO listed here, and that you can back calc right into those hand calcs to find that perforated. If you want, you can see the same type of, you have chords designed below here, and then you have the studs designed here, and you see that in the cross-section it gives you the same type of information with the chord design on each edge with the compression. If there was a hold down required, it would give us that. The wall, for this perforated opening, you go to an opening report, and here it'll design this opening for us. So we're going to see what the header requirements are. We're using a very large header. It's 6 by 8, I think we said. So here's a 6 by 8, so it's pretty big. You're getting at 0.17 unity check. I wouldn't imagine that would fail unless we had some serious point loads coming through. So you've got the openings listed there. Now, force transfer around openings is that last option we said is very similar reporting that we saw for perforated. There's no such thing as a region report. We are just looking at the wall as an entire wall. But what is interesting about force transfer around openings is its opening report is very different. So this is where all the work gets done in a force transfer around opening, is in this opening report. And as I mentioned, that those 8 segments or portions there are going to be designed individually, and they're broken up into 8 pieces. We have all those numbered out around the opening, and we say that we call those actually block numbers in this report here. So block number 1, we can see what the unit shear was across that. We can see 2 goes up here, 3, 4, and you can see what, as you look at this here, what the maximum is. So you can see, let's see what a larger one for us. This is a kind of a lightly loaded wall, but we see it looks like maybe 3.1 is the higher number I have here, 31. Pounds per foot running across that, so that's your worst case, and that's maybe in the 2 element right here. And so when we go back, and this header gets designed just like it got designed in a perforated. But here, this is the meat and potatoes of this wall, is this analysis summary. You find the maximum unit shear happening across each one of these regions, and then you pop back into the wall, and that's max unit shear. That 0.03 is what's being used to design the whole wall panel, and that you can see that's being that 0.03 number there, kips per feet is what we use, and then design to find that sheathing requirement there. So you've got force transfer around openings listed in this one, and this is a real good tool to see that. Force around openings is what I would suggest in there. Now this is all broken down in the results there. You can always see that listed right there in our wall panel designs. You can always go over to in-plane and look at the axial on the in-plane and see how these calculations are done. Just the shear check gives you a quick number, the governing load combination, and it tells us what the all the forces here are listed right on this spreadsheet. This is the best way to go look at a snapshot of what's happening. So I want to, before, we're running over time, but I want to show you guys one more thing just before we leave, a quick and easy way to go bounce back and forth between our structure. So if we take a quick look at one of these wall panels, I'm going to just kind of pick a wall panel in particular, or maybe just an edge panel here in this direction. We see that if we look at the region of this wall panel, we see that it's got 9 kips of the shear in this wall panel. And this is, we only have one region, and that's what's happening in this outer wall. And we have a flexible diaphragm. So if I switch this diaphragm on this lowest level maybe just to be this is going to be the 12-foot location, just to be a rigid diaphragm. It's as easy as toggling between a rigid and a flexible diaphragm. That's all you have to do. And you can just solve the same combinations. I'm going to solve those 2 combinations. And what it did is now I'm now designing that lower level with a rigid diaphragm. It might be common that you want to run an envelope, and that's all you need to do is just flip between a flexible and a rigid and rerun the model. And now you have an ability to go to a rigid diaphragm and see how the loads distribute differently in a rigid diaphragm. In this case here, so we didn't change the upper floors. Maybe you change all of them at the same time. That might be a little bit more logical. I just wanted to show you a representation on one level, how that might affect it. But also, you can have cases where buildings will have rigid diaphragms on certain levels and not on others. For example, maybe you have a rigid you can assume rigid all the way up the structure until you get to the very top and your roof is flexible. That might be a common case too. So we can go ahead and take a look at the detail report and have this same wall that we were using as a representation. And first of all, it got designed differently. For sure, that's a number one thing. That's a 15/32 inch thickness. And let's take a look at the region here. So we see slightly different things happening in this. The shears, we saw 9 and change. We see 8 and change here. We're going to see some different loads coming down the structure. So maybe we're seeing a little bit different axial. We're seeing loads change in here. Not a significant amount, but enough that it's changing slightly. And there's some reasons why we want to see it change across the board. So we're going to see, and when we do go to a rigid diaphragm on that lowest level, what we do get is we don't see those distributed loads anymore because physically they're not there anymore. What we're doing now is we're telling the program, instead of using that area load or transient area load, just use that wind load in the X direction, which we said was there, that 63 kips there, wind load in the X direction, is dropping directly into our diaphragm level. So it's now going right into that rigid diaphragm, and that rigid diaphragm is now saying is distributing it based on its stiffness. So when you want to see what's going on in each wall, take a look at the detail report, and you can then see what gets attributed to each wall. So you can kind of click on each wall. Let's see here. I don't know that we changed much, but I don't know if I'd remember much about these walls, what we forces were, but these openings here, we were seeing everything seems to be designing. This is still 3/8 inch panel. We looked at all of these here, and we still see 3/8 inch panel for all of these. But you might start to see different design for rigid versus flexible. So it's as easy as toggling that back and forth. Once you've got all your model laid out, you've got all of the structure defined, you can save that model. You can go ahead and save this as a name here and go back into RISAFloor. All of the loading here in RISAFloor gets maintained. Everything you did in RISA 3D, if things got sized up, like if these collector beams were sized up according to what happened over in RISA 3D, that would be maintained here in RISAFloor, and you can start to design the building based on what you've got for the entire structure. So the last piece of that, which I won't have time to cover today, but you can also take this whole model over into RISA Foundation and design for both gravity and lateral design over in RISA Foundation.